Hi, we're looking at exponential growth and decay. This is a little bit of a review, and then we're going to look at two new models in probably a different video. Okay, so different types of growth and decay models would be like, we saw compound interest, population growth, the saving for the iPhone. So the equation that we're going to use now is y is equal to a times e to the bx or the rx or whatever variable you apply, where a where b is greater than 0. The initial value is a, and e to the b is the growth rate, and the um and oh, you know what? It's really just b is the growth rate. And then the graph looks like something like this. We have y is equal to 0 as our horizontal asymptote, and our y-intercept is 0, comma a. All right, and it's increasing. So, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? So, first, let's take our 2 points, 2, comma 100 and 4, comma 300. Just like in class, we're going to write those in equations. So, we have 100 is equal to a times e to the b times 2. And then we have 300 is equal to a times e to the b times 4. We're going to take one equation. I'm going to take the first one and isolate for a. So I get a is equal to e to the b, the 2b, sorry, 100 over e to the 2b. Okay. Then we're going to substitute that into the other equation. So we're going to go ahead and substitute it right here. So we get 300 is equal to 100 over e to the 2b times e to the 4b. These are going to cancel, leaving me with 2b here. So now we have 300 is equal to 100 times e to the 2b, divide by 100, and we get 3 for 3 times the population is equal to 2, e to the 2b. And then how do we get the exponent out of the exponent? We ln both sides. So ln 3 is equal to the ln of e to the 2b, or snail, okay? And the 2b comes to the front. So we get the ln of 3 divided by equals 2b times the ln of e. ln of e is 1. So b is equal to the ln of 3 over 2. So that is our rate right here. Okay, we're going to hold on to that for later. Okay, like now later. And what we're going to do next is solve for number 2. Okay, we're going to solve for a using b. So we have this equation. A is equal to 100 over e to the 2b. And so that's 100 over e to the 2 times, and I'm going to stow this number as, we need to stow. I'm going to store this number as a. Okay, so I get e to the ln 3 over 2. Those 2's are going to cancel. Okay, leaving us with looking for my word. A is equal to 100 over 3, because the 2's cancel, and then e to the ln here, e to the ln of 3 is just 3. Okay, so I get, next we're going to substitute that back in. write the equation. Okay, so y is equal to 100 over 3 times e to the ln 3 over 2 times x. All right, and then the last thing, I think it asked me for how many fruit flies there are on day 5. Okay, so day 5. I have y is equal to, day 5 is equal to x, so 100 over 3 times e to the ln of 3 over 2 times 5. And when I get that in my calculator, I get about 520 flies. Okay, we're going to look at exponential decay next. This is another model that we use exponentials in. Okay, so some examples are like car depreciation, radioactive decay, and population decay. So the only difference in the equation is that it has a negative b. So when we define that the rate is negative, then we have to say that the actual value of the rate is going to be positive, and then we slap on the negative sign. Okay. The graph is decaying. It looks much like our other graph, but it's horizontally reflected. All right, so this one's a little crazy. In living organic material, the ratio of content of radioactive carbon isotopes, carbon-14, to the content of non-radioactive carbon isotopes, carbon-12, is about 10 to 1 to 10 to the 12. When the organic matter dies, its carbon-12 content remains fixed, while its radioactive carbon begins to decay with a half-life of 5,715 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time. So the ratio is equal to 1 over 10 to the 12 times e to the negative t over 8,245. So this one, the formula is given. And so what we're going to figure out is the ratio of carbon-14 to carbon-12 is in this newly discovered fossil is the ratio 1 over 10 to the 13. Estimate the age of the fossil. So all we're doing, so that we already know the ratio, we're just going to plug it in. Okay, so I have r is equal to 1 over 10 to the 12 times e to the negative t over 8,245. Okay, so our r value is 1 over 10 to the 13 is equal to 1 over 10 to the 12 times e to the negative t over 8,245. All right, multiply both sides by 10 squared, or 10 to the 12th, sorry, times 10 to the 12th. And I see that everything here except for 110 cancels. So I get 1 over 10 is equal to e to the negative t over 8,245. Now we have our exponent by itself. Exponent is isolated. The exponential equation is isolated. So we can go ahead and take the log of both sides or snail this. So I'm going to do the ln of 1 over 10 is equal to the ln of e to the negative t over 8,245. And this is going to go to the front. So we get the ln of 1 over 10 is equal to negative t over 8,245 times the ln of e, which is 1. Multiply both sides by 8,245. And we're left with 8,245 ln of 1 over 10 is equal to negative t. multiply both sides by -1. -1. So I now have, I'm going to go ahead and move up here. Just kidding, okay. So now we have t is equal to -8,245 ln of 1/10, which is about equal to 18,000 years, 985 years. And we're going to take a break there, and we're going to start on another video after this.